Hi class, sorry, just gonna get my camera ready here. Today we are talking about concavity and points of inflection. So this is the last note you will need before we get to full on just curve sketching. So we're gonna learn our last techniques here today. So we're going to primarily learn something called the second derivative test, which tests for concavity in functions. Okay, so concavity basically means is it curved up? That's concave up. Or is it curved down? So is it concave down? So let's break out why the second derivative helps us tell if a curve is concave up or concave down. So I'm going to draw half of a concave up curve here and then put arrows on the end. Okay, and then the other half of a concave curve up going here. So both of these sections of a function represent a concave up section. Okay, so if we draw tangents very carefully, so think about what is happening to the tangents to the size of how big the slope of the tangent is and what that means for the derivative. Okay, so in these sections, so we'll call this point A, and we'll call this, we're at this point of tangency, point B, and this point of tangency, point A, and this point of tangency, point B. Okay, so what is happening here? Well, on this interval, actually, you know what, let's go to this one first on the right. On this interval, from A and B, the slope of the tangent is increasing, okay? So here it's more shallow, so that would be a low positive number, and here it's steeper, so that would be a higher positive number. So you can see that the slope of the tangent is increasing. Okay, so that means over here, this is a little bit more difficult to think about, but the slope of the tangent is also increasing in this picture because this is, yes, it's steeper, but that is a more negative number. And then this negative slope is less negative. So the actual value of the slope of the tangent is increasing. Like this could be -10 and this could be -2, for example. So in both of these cases, the slope of the tangent is increasing. And remember, when something is increasing, then that means its derivative is positive. So since we're saying that f prime, which is another way of saying slope of the tangent, so since we're saying f prime is increasing, that means that the second derivative is positive. Okay, and that's what it basically says up here. So if a graph is concave up on an interval, then that means that the second derivative exists and the second derivative is greater than 0. Okay, the graph is above the tangent at every point in a concave up section. All right, so again, if a graph is concave up, that means that its slope of the tangent is increasing, which means that the second derivative is positive. All right, so now let's analyze concave down. So similarly, we'll draw two sections of graph that are both concave down. Okay, and we'll draw tangents. So try my best. I hope you guys are using rulers when you do this. I'm actually drawing a legit tangent. It's a bit tough on my trackpad, I apologize. I know it's not great. Okay, so these red lines represent tangents. And obviously, we're thinking about the slopes of the tangents. That's the rate of change. So on an interval from A to B, where A to B is left to right, these are both concave down. So notice that the tangents are all above the curve. So the curve is always below the tangent. So what is happening here? Well, f prime, or the slope of the tangent, is always actually decreasing. Okay, so notice here, it's a high positive number and then a lower positive number, and then you have, a low negative number and then a very negative number. So over this entire interval, f prime is decreasing, so that means that the second derivative is negative. Okay, so if the graph is concave down, that means the first derivative is decreasing, which means the second derivative is negative. Okay, so if y equals f at x has a critical point at x equals c, so f prime at c equals 0, then the behavior can be analyzed with the second derivative test. So we use the first derivative test to see what type of behavior was going on at a critical point, to find if it was a max, a min, or neither. So now this is just another way of doing the same thing. So it's not always necessary in addition to the first derivative test, but sometimes we do the second derivative test instead because it's more simple. And you'll see an example shortly where we want to find the second derivative anyway, so we're not actually creating more work for ourselves. So the second derivative test tests the same thing as the first derivative test, just in a different way. So basically, if you find that you have a point C, okay, and you know that it's a critical point, it's a local minimum if it's in a concave down, sorry, a concave up section. So if the second derivative at C is positive, that means you know you're in a concave up section and you're dealing with a minimum. Okay. Similarly, for something to be a maximum, you have to be in a concave down section. So if f double prime, so your second derivative at C is negative, you know you're in a concave down section, so therefore this has to be a max. So remember, you've already identified C as a critical point, okay? And then you can just test, well, is the second derivative there positive or negative? And that will tell you if you're a concave up or down section, and then if it has a max or a min, okay? If this is one problem with the second derivative test, okay? If the second derivative is 0, the nature of the critical point cannot be determined without further work. Okay, so now we get to learning about how we can find points of inflection, which I've talked about finding, so now we can finally do that. So a point of inflection occurs when basically a function is changing concavity at that point. So right at that point, we'll call it C, the function is changing from a concave down to a concave up section, or a concave up to concave down. So for example, if you draw something like this, okay, basically a cubic shape, and I'll change the color here for you. So right here at C, and here's F at C, basically in this section, it's concave up. So in this section, F double prime at C, sorry, I should just say F double prime is positive. And over here, this is a concave down section. So over here, F double prime is negative. So we're switching concavity. So notice that the function is always increasing over this interval. So therefore, the first derivative will always be positive, but the concavity changes. So that's why the first derivative is not enough to find points of inflection. So if you want to find points of inflection, you have to do the second derivative. Okay, again, the function's always increasing, so the first derivative is positive over this entire interval, but the second derivative changes from negative to positive, showing a change in concavity. Okay, so we can also show kind of a different relation going the other way, so where it changes from concave up to concave down in this case. So there's going to be one point exactly where that concavity changes, and so the second derivative will allow you to find that. Okay, so in this section, F double prime is positive, and in this section, F double prime is negative. So notice here that the function is always decreasing. So your first derivative will always be negative, but your second derivative changes from positive to negative. So all points of inflection must occur where the second derivative is 0 or the second derivative is undefined. So there's 5 major points there. That's the major learning. Now from here on in, it's just applying it and doing examples. So if you want to take a note of the time of the video, this is where we start with the examples. So we're going to sketch this cubic using our first and second derivative. So the first thing you want to do is find the derivative. So we get 3x squared minus 6x minus 9. Okay, so I'm going to factor that. So common factor out a 3. And then after you do that, you can find the factors of x minus 3 and x plus 1. So I just skipped a step for simplicity here. Okay, so let's think about this curve before we even think about the derivative. It's a cubic. It's an upward facing cubic. So we already know that it's going to have a concave down section followed by a concave up section. We know it will always be increasing, but we know there will be a point of inflection, so we want to find that, okay? So don't be afraid to let your common sense about what you know about this function guide you along the calculus, even if the calculus is required for the question. So now we want to set the derivative to 0 to find any critical points, okay? This will bring us back to our critical points, which is the points that make the derivative 0 or undefined. So in this case, we have x equals 3 and x equals -1. Nothing makes the derivative undefined. Okay, so notice that it says critical points, so we actually need to go and find these y values. So I went and found them, and so the point for 3 is -17, and the point for -1 is 15. So remember what this means. These points could each be a local max or a local min. Okay, because they make the derivative 0, so that means that the tangent is horizontal at these x values, okay, which means that it could be changing direction there. So I'm just going to change color for this next part to find the second derivative. So we look at our first derivative and take the derivative of that. So we get y equals 6x minus 6, which we can common factor to 6 bracket x minus 1. So set the second derivative equal to 0 to find all points of inflection. So 6x minus 6 equals 0. We get x equals 1. Okay, so x equals 1. That gives us the point 1, -1. This could be a point of inflection. We're going to actually have to check that the concavity changes. Okay, be careful not to put POI because POI means point of intersection. So if you're doing your own short form, at least put INF or something for inflection, even when you're doing your homework, just so you're not tempted to do that on the test. Okay, so we're going to examine the second derivative on intervals determined by step 4. So make conclusions about concavity and if each critical point is a max or a min. So we're going to look before 1. And we're going to look after 1 because that's our point of inflection. And we're going to look at the second derivative. So the second derivative before 1 is, think about it, you would have like a smaller number than 1 being subtracted by 1. So it's negative in this section. So that means that we have a concave down section before 1. So it looks something like this, right? And after 1, okay, if we put in a value of something greater than 1 here, you get out a positive result. So that section is concave up, so it looks something like that. So that means here at, I'll change the color, x equals 1 right there, because it changes concavity, that is a point of inflection. Yay! Now, what does it also tell us about our critical points? 3 and -1. Well, -1 is an x value that's less than 1. So that means that -1 is in a concave down section, which means that that is a local max. And 3 is in this section. 3 is larger than 1. So the point 3, -17 is in a concave up section, which means it must be a local min. So that's the second derivative test, that we're using the second derivative to make determinations about critical points rather than checking the behavior of the first derivative. Okay, so the second derivative test is helpful in this case because it actually is faster than the first derivative test, and we were going to find the second derivative anyways to find the point of inflection, so it wasn't any extra work. So as you go forward with your homework and with your curve sketching, you'll start to realize that sometimes the first derivative test is easier and sometimes the second derivative test is easier, because sometimes the work to find the second derivative isn't always worth the amount of time it takes. Okay, so I'm just making my grid here. I'm going up by 1s on the x-axis, and I'm going up by 5s on the y-axis. Okay, and I'm just going to do a different color, because why not? Okay, so we have the point 1, -1. So that's your point of inflection. Then we have the point -115 as a local max. And we have the point 3, -17 as a local min. Okay, and so now, and our y-intercept is 10. So now you just want to be careful about how you draw the concavity. So I usually start from the point of inflection and go up and back down again. We didn't find the x-intercepts, but we could have. When we're curve sketching, we will. And then I start from there again and go this way, just so I can really show the change in the concavity. So that's a trick you might want to write down. Once you know your point of inflection, when you're drawing it, always start from there and go backwards and forwards. Okay, and then you would want to label all your key points. All right, so there we go. So let's take a look at what happens with something like x to the power 4. I think you guys all know what x to the power 4 looks like. It's basically like a wider quadratic function. Well, it's wider, closer between 1 and -1, and then after that it's steeper. So but it's similar to a quadratic look. So let's see what the first and second derivative can tell us in this case. So we notice that the intercept is 0, 0. We can kind of think about what this function looks like. And then we want to head into finding the first derivative, so 4x cubed. So we can see that 0, 0 is a critical point. Critical point since f prime at 0 is 0. Okay, and we got this 0 from putting it back into the function. So that tells us that we have a critical point. So let's go to the second derivative, 12x squared. So this tells us that f double prime at 0 also equals 0. So therefore 0, 0 is also a possible point of inflection, but not necessarily. So we have to go through and check the second derivative. So before 0, what's happening to the second derivative? Well, the second derivative is positive, right? Because you're putting in a number, you're squaring it, you're multiplying it by 12. And after 0, the second derivative is also positive. So this tells us that there's no change in concavity. So what does that tell us? Well, it tells us that 0, 0 is not an inflection point. So it's not a point of inflection. Okay, so since f prime at 0 is 0, it's either a local max or a local min. Okay, and since that should be 0, and since the graph is concave up over its domain, we can actually conclude that x equals 0 is an absolute minimum. So it means that's the absolute minimum it goes in its whole domain. So you can graph quickly what this looks like. It basically just looks like a quadratic. Okay, and there's a point 0, 0. All right, So that's an example where the second derivative is 0 at a point, but it's actually not a point of inflection. Okay. This is a really interesting looking function, and calculus will definitely help us analyze it. So if you can't read that very well, that is saying x to the power 1/3. That's what that says. Okay, so let's think about this. This function exists everywhere. It has no restricted domain. It has an intercept at 0, 0. Okay, I just want you to think about, like, what do you know about this function? Think about it. When x values are positive, the y values will be positive. When x values are negative, the y values are going to be negative. So that's something to think about. You know, just kind of play around and think in your head, what do I know? And then calculus should help inform your choice of how to graph it. So let's find the first derivative to help us find any critical points. So we take down the 1/3, and then we have x to the negative 2/3, then just times 1 using the chain rule. Okay, so that can be simplified to 1/3x to the 2/3. Okay, so notice that, I'll change the color here. Notice that f prime at 0 does not exist, but f at 0 does. So remember, what does that tell you? That tells you that it's either a cusp or a vertical tangent. So we have to do some work to figure out if it's a cusp or it's a vertical tangent. And if you remember that from a few notes ago, we have to apply the first derivative test to find that out. Okay, so we're going to apply the first derivative test. And if the function is changing from increasing to decreasing, or vice versa, then that's a cusp. But if it's changing from increasing to increasing or decreasing to decreasing, that's a vertical tangent. Okay, so before x is 0, so when x is less than 0, what is f prime? Okay, so if you put that in, you get that it is positive. Okay, if you put in any number and you square it and then take the third root, it's positive. So this is always a positive result. Same can be said for after 0. Your first derivative will be positive. So because it's going from increasing to increasing, we know that this is a vertical tangent. Okay, x equals 0. Okay. So we also know that f prime, we also see that f prime is positive for all x in the set of the domain. So therefore, what does this tell us? This tells us that f is always increasing. And that tells us that there is no extrema. Okay, because we never change from increasing to decreasing, so we never get any extreme or local values at all. Okay, since the function is always increasing because the derivative is always positive. So now let's go ahead and take the second derivative and see what that can tell us about this function. So we bring down the negative 2/3 and multiply it by the 1/3. So that gives us negative 2/9. And then x, and then we have to take our exponent down another whole 1. So that gives us negative 2 all over 9x to the 5/3. So that means that 0, 0 is a possible point of inflection. So it is a vertical tangent, but it could also be a point of inflection since it makes the derivative, the second derivative, 0. So 0, 0 could be point of inflection, again, because it makes the second derivative 0. So now we employ the second derivative test to see what's going on here. So when x is less than 0, what is going on with our second derivative? Well, in this case, you would get a negative number on the top, but also a negative number on the bottom if you put in a negative number here. So that actually gives a positive result. So it's concave up there. And then when x is greater than 0, you get f double prime is negative on the top, but positive on the bottom. So that's a negative second derivative. So that section is concave down. So that means that x equals 0 is a point of inflection, and it has a vertical tangent there. So it's both. So what does that look like? Well, this is how we graph it, but then we can also go to GeoGebra and take a look so you have a more formal version for sketching it, because I'm running out of room here. So basically you have this point 0, 0. Okay, and you have this concave up section that's coming from here, but remember, it doesn't go back up. So it's concave up even though it's increasing the whole time. So it wouldn't go back up because then you would have a section where the function was decreasing, but our first derivative said that our function is always increasing. So it's going to look something like that. And then right here, it's going to go kind of vertical and then go like this. So again, always increasing, but concave down. Okay, so that is what it looks like. If you go to GeoGebra, sorry, I should have set this up ahead of time. I apologize. Just take a couple extra seconds. Get a drink of water or Diet Coke. And tell your favorite math joke. I don't know, maybe, I don't have one. This is taking longer than expected. Okay. X to the power of 1. Oops. 1/3. So there you go. That's what it looks like. Okay. So again, that section here, it's concave up, but it's always increasing. And then right here, we would have a vertical tangent, but it's still a function. And then it changes to concave down, but it's always increasing. Okay, and calculus allows us to find those features. Okay, one more example, example 4. So this is a rational function, obviously. So I'm not going to lie, finding the second derivative isn't fun, but we can do it. Just bear with me. So let's determine the points of inflection. So first we have to get the the first derivative before we can get the second derivative. So remember, it's the bottom times the derivative of the top, which is 0. So then minus the top times the derivative of the bottom, which is just 2x. So that's how you get the numerator all over the denominator squared. Okay, so notice that so f at 0 is defined. Okay, and f prime at 0 equals 0. So therefore 0, 0 is a critical point. Okay, because it makes the derivative 0 and it's defined in the function. So that means it is a critical point. So there you go. There's nothing that actually makes this function undefined. There's nothing that makes the the denominator 0. So this is the only critical point that we find, again, because the denominator will never be 0. You can also note that there's no vertical asymptote for the same reason. Okay, so now let's find the second derivative, which is just takes a bit more work because it's a nasty function. So we do the bottom times the derivative of the top minus the top times the derivative of the bottom. So now we need chain rule, right? So 2x squared plus 3, 2x is the derivative of the bottom. And then that's all over the bottom squared. So x squared plus 3 to the power 4. Okay, so now it's just a matter of using your beautiful, wonderful, awesome ability to collect like terms and all that kind of fun stuff. So what you might notice first is that you can actually common factor out an x squared plus 3. And the reason why that's useful is because then you can cross one of these x squared plus 3's out. So when you common factor out an x squared plus 3, you're left with x squared plus 3 from here, because there was 2 of them. So when you take out one of them, you still have 1 left, and the negative 2. And then from here, we take out, okay, so we already took out this here, if you want to see this. So when we common factored out, we took out this squared, and we took this out. So what are we left with here? Minus 2x times 2 is minus 4, times 2 is minus 8, but then plus a minus, so that gives us plus 8x squared. Okay, because we common factored that out. Again, we chose to do that common factoring because that's what the denominator is, and that allows us to get rid of one of these. So now we can cross that off and make this a 3 instead, and we can collect like terms here. So you end up getting 6x squared minus 6 all over x squared plus 3 to the power 3, and that's your second derivative. So now we want to set that second derivative equal to 0 in order to see a possible point of inflection. Ooh, where's my marker? Okay, so I'm just going to do that over here because I'm running out of space. So where you set f double prime at x equal to 0, you get 6x squared minus 6 equals 0, and you solve this, and you get x is equal to plus or minus 1. So we have 2 possible points of inflection, at positive 1 and at negative 1. So let's check on either side of them. So we've got to check less than negative 1, greater than negative 1. Sorry, I should say, erase that. Between negative 1 and positive 1, and then greater than positive 1. So we're checking the sign of the second derivative in each case just to see if it's positive or negative, to give us some information about the concavity. So f double prime. So when x is less than 1, this is a positive number on the top and a positive number on the denominator. So that's a concave up section. Between negative 1 and 1, you get a negative number on the top with a positive number on the bottom. So overall, that is a concave down section. And greater than 1, again, it's positive over positive, so you get a concave up section. So let's interpret that now within the context. So that means that x equals negative 1 is a point of inflection because we changed concavity, and x equals 1 is also a point of inflection because it changes concavity. But what about x equals 0? We found it was a critical point at the beginning, so we know that x equals 0 is actually an absolute maximum, okay, because it's in a concave down section, and the derivative, sorry, and it's concave down in these sections, and we don't have any other maxes or mins, so it's not going to be turning back up because we only have one critical point. That's the only critical point. So that is the absolute max. So how can we take this information and turn it into a graph? Well, let's label the important points here. So we have the point 0, what was it? I said it was 0, 0. That was not right. That should be 0, a third. Because when you put in 0 here, you get a third. So this is the point 0, a third. I'm going to make it up here. And here's the points at negative 1 and positive 1. So basically this section is concave up, and then, sorry, concave down. And then these sections are concave up, approaching the asymptote of 0, since it was a bottom heavy function. So that is how that function looks. Okay. If you have questions about the analysis that I did here, please ask me. Again, the first derivative will tell you if there's possible maxes and mins. The second derivative will tell you points of inflection, and it can also tell you about maxes and mins. So you really just have to think about what each point of information gives you. Sometimes you won't need the second derivative test. The first derivative test will be enough. And sometimes it's helpful to go through and do the second derivative test to get a full idea of what's happening with the function. So here you go. Here is your summary of the second derivative test. If your second derivative is positive, then it's a local minimum because it's concave up. If the second derivative is negative, then there's a local maximum there because it's concave down. And if the second derivative is 0, then the test fails. You can't use it. You need to use the first derivative test. So thanks for watching, guys. Hope you learned lots.